Hello, everyone. Thank you for having me. My name is Raphael. I am situated in the Netherlands. I have been invited to this first edition of the Conf to talk about a topic that is dear to us at Cockroach Labs. And it's going to be around error handling. So my name is Raphael. My internet handle will be Kena or KNZ, depending on the platform. Feel free to reach out to me after this presentation. The topic of this talk is very close to a topic that most Go programmers are very acquainted with, and that is the error handling in applications and distributed systems. Error handling is probably a undervalued topic of conversation that is pervasive. That is a very important topic, but that is not exactly pleasant necessarily to work with. And the reason is that the moment where it becomes relevant in programs is a moment where things happen that we would prefer not to happen. So as we work with distributed systems, especially CockroachDB is a distributed system, unfortunately, errors and situations or forcing situations are a necessary fact of life. And so this is a topic that we have invested extra in because it is completely unavoidable the moment the system is distributed. The entrance here is these pictures that I pulled from the tour of Go. The idea is that errors are objects in Go and that they implement a particular interface, and that the idiomatic way to check for errors and propagate them throughout Go code is to verify the return value of functions, check whether there's a return an error, and maybe do something with that. It is the case, though, that we have not been very satisfied with this throughout our work. And so today we are going to investigate a little bit whether we can do better. And the two angles that I will cover today are performance and programmer productivity. The invitation for this talk is more or less related to a piece of research that I started in 2018 about the algorithms used in the Go compiler to generate low-level machine code. I was particularly interested to understand how Go differs from C++ and other languages that use a more traditional approach and quantify this approach. And this really brought me very quickly to the topic of error propagation, because Go does things that are a bit different with regards to parsing arguments and returning return values, and having return values for errors throughout the code base. I found it interesting because it looked to me that it would behave differently from using exceptions, which is a regular common word for what Go calls panics or panic objects. So you see here two different, on the left and the right, two different approaches to do more or less the same thing, where you have a program that performs some computation that are maybe resource intensive, and where the moment where an error happened doesn't matter as much as interrupting the entire computation when something goes wrong. So you see here the pattern is the error is, sorry, the unit of work is in a loop, and then there might be an error, and then the loop must stop. And so in one case, we have to check that every time. In the other case, we can set up an exception handler before we enter the workload, and then if something happens, that will be caught by the handler. If nothing happens, then we don't pay any extra. And so I went on back in the days to evaluate empirically how much this would differ in practice. So the bird view of the results is summarized in this diagram. You see here a diagram with the x-axis is the amount of work performed under the API interface, if you will, the place where we want errors to be reported. And on the y-axis, how much time the computation takes. In the particular examples of the program on the previous slides. And the baseline in the curve that is blue for people who can see colors is also the curve that is the lowest on the diagram, is where the code would not perform any kind of error checking at all. And so what you see in this diagram, that's the main message with regards to performance, is that if you use exception handling, there is an initial cost in Go to set up an exception handler that is on the order of a few nanoseconds. But once that price is paid, and it's a fixed price over time and over an amount of work, it gets amortized. And in the particular case of Go, this is actually a very low price. And even for an extremely simple program like the one we saw before, the payoff comes at a very small amount of work. In this particular case, just 6 iterations of the loop is sufficient to amortize the price that is paid at the beginning. And in general, in fact, if we measure more at a larger scale, the cost of moving values around, in particular, moving a return value around for error handling, we see that it's a price that is pervasive in a Go code base. So as functions are called and returned, and those return values are passed around, they actually have a pervasive overhead on the performance of Go code that is, in this particular case, between 3 and 5%. But in other codes that I've studied, is between 1 and 10%, depending on the balance between function calls and computational workload. So the message that I was trying to convey back in the day is that calling conventions matter. This is something that the compiler generates for every single function body and every function call. And this is therefore something that is not part of the main body of computations and therefore cannot be really optimized away. This is also something that differs in Go compared to other languages. In particular, in Go, there was a choice made to use memory operations as opposed to machine registers. This is inherently slower. On x86, the processors are really making a best effort at trying to erase this difference, but anything else really will make an extremely strong difference between the two. And so Go is taking the longer route here, and that really comes up in the results. And the other part of it, of course, is that having work done at every level in a call tree is an overhead that just is not there if we were to use a exception handler at one location that is well placed to amortize whatever work comes underneath. Another aspect here that is not as much considered in small applications, but at the scale of a large program like CockroachDB becomes relevant, is the size of the code segments in the executable form. When the binary program that you're running is larger than the CPU caches, then it actually costs extra time to fetch code in and out of the processor, and that's noticeable and very measurable. And having code that is literally bloated by overheads in machine instructions makes it more costly because of those moving in and out of instruction caches. So I was, after I did this research, reminded that the Go team has started a project to introduce a register-based calling convention, and that maybe these results that I just presented would be invalidated, or at least would be modified. And here is a link to this issue 4724, and it's been approved. There's a tentative schedule to have it released in 1.16. I actually don't know about this timeline exactly, but it is probably going to happen, at least for x86 and ARM, and maybe other platforms. That being said, even if we can expect 1 to 4% performance improvement generally throughout all Go code, it is still the case that we will have extra machine instructions to pass data around. More return values means more instructions to move this data around. And an instruction executed is more work than no instruction executed. So the main essence of the argument that this idea of amortizing the cost of error handling is fundamental, remains regardless of the calling convention that is being used. So here, I'm going to page out a little bit of the argument of performance because the reason why this started to matter much more concretely for the CockroachDB project was a matter of programmer productivity and software quality. So what happened is that we were looking at this kind of code, and you see on the left here, not only do we have error handling, but we are very much dependent on a a repetitive pattern to check the error to be, whether there is an error object and then what to do with it. And then what you can see in this example here is that there are two parts that are completely critical to have correct programs, and that is that the conditional remains correct, that we don't compare error with something else or something wrong, and that the propagation of the error also works properly. And that is, in fact, a pain point. I will come back to that in a second. Another aspect is the sheer amount of repetition that goes through a code base. You can imagine that we have functions in Go code that do different things. Like functions typically will have multiple control steps to invoke other services or the functions. And there is, of course, a composition of functionality. And then every time we use error handling with return values, that means that the verification of those error objects is repeated throughout the function body. And as we all know, in software, repetition is a source of mistake. Not all things are created equal, and humans are very much prone to mistakes. And code that doesn't exist is code that cannot have mistakes. And so what you see here very clearly is that you have here on the left more opportunities for mistakes than on the right. And there is another very basic aspect to this as well, which is the sheer complexity, like the amount of text that need to be read and evaluated when analyzing code and trying to maintain it is just larger when there is more code written. It sounds very trivial, but in fact, it's not completely trivial. If we look at the CockroachDB project and we look at just the code that has been written by humans, I mentioned this because we also have an extremely large chunk of automatically generated code using preprocessors and internal compilers for CockroachDB. This is 14,000 plus occurrences of error checks in the code. And it was unavoidable multiple times. We had mistakes where the conditional was not the right one, or an error was not propagated when it should have been. What this is really clearly a correctness bug. And the issue here is really not trivial, because error return paths are not as well tested in most software as the positive path where there are no errors. And therefore, the correctness of these conditionals is important for product stability and quality, because the moment something goes wrong, the last thing you want is the program to pretend nothing happened, or the other way around. If you run into an edge case that should work and then the program mistakenly returns an error when it shouldn't, that is also something that the user will be uncomfortable with. And well, there is no choice for this here to have linters, because the Go compiler is not helping us with this. The Go compiler doesn't really know whether we intend inequality where we want a difference instead. So that has been a source of headaches, a source of pains, a source of bugs, including production outages in 2 cases for customers, and that was extremely unfortunate. So that's the reality of a large system. To come back to the topic of performance, we have a couple of areas in CockroachDB which are performance sensitive, and it is unfortunate, but Go doesn't have a very good external foreign function interface to interface with other languages, and therefore, for performance sensitive code, it's kind of a non-starter to try to say, let's re-implement the performance sensitive parts in a different language that is performance oriented, because the interface with Go, will offset that benefit. So we have to make do with Go for performance sensitive code, and therefore we have an interest in optimizing Go code for performance as well. And therefore, when we look at this error handling and we see 1 to 3% performance on the tables, that is something that gives us pause. So what has happened in more and more components in CockroachDB is to switch over to use exception handling instead of error propagation. And we have a discipline about this. So here you see an example of an API inside CockroachDB between 2 components, the optimizer, the query optimizer, and what we call the query executor that is handling transactions and so on. And that API is really an interface between 2 different teams, 2 different engineering teams. And that API continues to use explicit error returns, because we believe still in this very strong message that the errors that a function returns should be part of its external interface. And so we continue to value this idea that interfaces and APIs between components should return errors. However, immediately under this, within a package, we decided that it would be much better for correctness, simplicity, and maintainability to have the other mechanism using exceptions. And we have this pattern coming over and over, where the API entry point has a well, the Go variant of a try-catch block with a call to the recover function, and then a conditional on the type of panic that is returned. And so if you look into this function, you will see two different conditions that we verify to treat a panic as an error. First of all, it needs to be an error object. Why this matters is because if the Go runtime detects an internal inconsistency, like there is a garbage collection error or a segmentation violation or invalid pointer access, it will throw an exception of type string, and that is not an error. And we want those exceptions to be propagated and not be caught as part of the interface of a function, of a package. And the other part of it is that in some cases, the runtime will return an error object, but it also ensures that it implements the runtime.error interface. And so we can use, say, has interface method on a suitably written errors package to verify whether the error object we have in the panic or one of its causes, because now in Go 1.13 and later we have linked lists for errors, is implementing that interface. And if it does, then we can ignore it, or we can treat it in this particular case as an assertion failure, which is actually a message for the callers that something unpredicted happened. So that's the prose description of what I just said. This is now happening in multiple places in CockroachDB, and we are extending our usage of this pattern throughout the project. And what is extremely clear is that the development team is actually much more happy to work with the code base by having the code more compact, easier to read, and easier to learn. So that is a learning that I think it was worth sharing today. And for the benefit of the community, we have started to think about how to abstract this and maybe push those learnings into other projects. And so the starting point of these recommendations is to first start to understand that redundant efforts in programmer time is costly, and also sources of opportunities for mistakes and bugs and quality problems for software. So there is a very strong need in the Go ecosystem, and if possible, the Go language, to make error handling more concise in some way. So Rust, for example, has created that question mark operator that will be syntactic sugar for evaluating whether within a function body, functions that can return errors actually return an error and then immediately stops the control flow. And something like that in Go would already be a huge improvement. Of course, we could have that, but if we continue to use error returns at every single level of a call stack, we'll still have a little bit of this obfuscation of what functions are really about, because we see those return types everywhere in the signatures of the functions, and there is this performance concern. And so the message, really what we want to share here, is that control panics or exceptions in regular languages really are an improvement on software quality and maintainability. But with a little discipline, it is important that they don't spill over API boundaries, because that is a source of pain that other languages have learned and that we probably do not want to introduce in the Go ecosystem. So here is the main message here. Using exceptions within a package is really a plus for software quality and maintainability. But if we wanted to do that properly, we probably want to acknowledge API boundaries and remain within those boundaries, out of these boundaries, sorry, with error objects in the signatures. So finally, after I prepared this presentation, I was reminded by a teammate that hidden inside the Go standard library in the JSON package, it so happens that the JSON package already does this, and for pretty much the same reasons. I actually did not know this, and I found it extremely funny to discover this fact, and actually it has never been documented so far I know. And if we look at the code that would need to be put into the software, then here is an example of the code that would be close to what we use in CockroachDB, where reporting an error would be throwing an exception with the panic keyword, adding context to an exception, which is to decorate an error, because the error decoration is important for providing context. You can catch a panic and then rethrow it after it's been decorated. And the moment when you have an API boundary and you want to translate the exception into an error, then you need to recover it, check the type that it implements the error interface, and very much recommended, verify that it's not a runtime error from the Go runtime, because those are maybe symptoms of something that is happening outside of the code you've written yourself. And the beauty of Go and the defer keyword in Go is that we don't need to repeat this code over and over again. It's possible to have the recover keywords in a different function and defer that. And so what we really probably will have at some point in the ecosystem is libraries that look like this, with functions, helper functions that you can defer in your own code that will contain this logic and make it shared across many functions. You can have an annotate function that will add some decoration to errors, and you can have a catch function that will facilitate the translation of panics to errors. And if this pattern takes up, then of course, at some point, we could even consider abstracting this further and really make this a first-class deconstruct in the programming language itself. I understand that the Go language team doesn't really enjoys the, well, does not want to entertain the idea of adding exception handling. But if it was an incremental improvement because the community bit by bit is acknowledging that it's beneficial, then it might be a different story. So that's the takeaway for this story here. What can you do about this? Well, the number one message is really to understand and maybe acknowledge that all these error conditionals and error returns are software that is written and is possibly a source of bugs and mistakes. And we don't really have good tooling to prevent those mistakes or detect them after they've been made. And then also all these lines of code that exists in the Go programs, when a newcomer comes to a code base and needs to understand what's happening here, it might be okay when the program is just 100 or 200 lines of code. But if the project is sizable, think about Kubernetes, about CockroachDB, about TIDB, then it's a very different story. And then having every single part of a function body that matters with regards to behavior expanded into 3 lines of code because of the error handling around it, that is cost into the maintainability that is completely not negligible at that scale. And so what we really hope at some point is to understand that this is a trade-off that is not trivial, and that the idea of using exceptions or control panics under API boundaries is generally beneficial. And that could be acknowledged in our education materials in the Go community, starting with a tour of Go and hopefully throughout other tutorials. So this was the main message. And it is also the end of the story I want to share today. So thank you very much for having me, and I will welcome your feedback, engagement, and so on, especially if you want to reach out on Twitter or elsewhere after this presentation. Thank you very much. The slides will be made available, and there are some references in the slides that you will be able to find when you access the slides online afterwards. Thank you very much, and see you very soon.